So in this problem here, we're interested in finding Reynolds for a flat plate configuration. This is going to be important because further down the line, the track, what we want to do is, find the heat transfer for different geometries, and we know that the heat transfer is a function of the convective coefficient, which is a function of the Nusselt number, which in turn is a function of Reynolds. So this is a simple problem just to introduce this idea on using Reynolds and on finding properties at the property table. So at 30, air at 30 degrees Celsius in 2 atmospheres is flowing under laminar conditions over a flat plate wing of a model aircraft at a speed of 5 meters per second. So 2 atmospheres, we definitely want to highlight that. The molar weight, molecular weight probably is better. The molecular weight of air is M-air is 29 grams per mole. Determine Reynolds number at a distance 30 centimeters from the leading edge of the plate. So we learned already that the leading edge is, the first, let's call it the first edge at which the fluid finds our flat plate. Fluid in this case is air, so we can write air straight off the bat. So this would be our leading edge right here, right? So we want to know what is Reynolds at a distance of 30 centimeters from the leading edge of the plate. So that's going to be our x for this problem. We have properties of air. We have T infinity, so let me put all that in green here. So T infinity is 30 Celsius. I'm going to go ahead and say that's 303 Kelvin because you can note our table, it gives us the properties of air in Kelvin, so that's in Kelvin. We have a pressure of 2 atmospheres. That's relevant because some of the properties are pressure dependent. We have the velocity, u or v, coming in at 5 meters per second, so that's the velocity at which this air is going over the model aircraft, the flat wing plate, the flat plate wing. And we have the molecular weight of air, which was given to be 29 grams per mole. Brilliant. So how do we do this? Well, we want to find Reynolds. To be able to find Reynolds, all we need to do at any given position, right? So in this case, we're trying to find Reynolds at 30 centimeters or 0.3 meters. So all we need to do is multiply the density, the free stream velocity, the characteristic length, which in this case is our 30 centimeters in meters, and divide all that by the viscosity. Now, this is all great. We have that. This we have. What we need to find are these two fellows here, which we're going to find in our property table here. So we're interested in 303, which is going to be somewhere between 300 and 500. So between these two numbers that I'm highlighting. And we're after the density, so this column here, and dynamic viscosity, which is this column here. So what we need to do is do a little interpolation. Obviously, if you're doing this on an exam, you'd go ahead and say, oh, the property is going to be very similar to 300 because 303 is very close to 300. But since we're doing this, with time, then we want to take our time to actually do interpolation for the properties that we're looking for. So we want this for 303. And then the density here is going to be 1.1774. Over here is going to be 0.998. And over here, the density will be 1.8462 and 2.075. Just watch out because this is to the 10 to the minus 5, though the negative there is very hard to see if it's there at all. So this is to the minus 5, and this is to the minus 5. And then the other thing that you want to be aware of is that these are for atmospheric pressure, so 1 atm, right? And then dynamic viscosity, conductivity, specific heat, and Prandtl, they're not strongly pressure dependent, so we can take them as they are in the table. However, our density is pressure dependent, so we need to account for that after we find the densities here. So after doing this integration, what I got here was, interpolation. What I got is 1.1666, and over here I got 1.8599. So about 1.6, that's fine. Times 10 to the minus 5. All right, so now this is the thing to watch out for because this guy is not pressure dependent, but the first one is, right? So this one, we need to, let's put a little star here. Let's put a little star to remind ourselves that we need to find that for 2 atmospheres because what we have now is the value for 1 atmosphere. So at 1 atmosphere, this is 1.1666 kilograms per meters cubed. Okay, now there are 2 ways to do this. I'm going to leave the first way on the previous video that we did before, which is very similar to this question, and that's one way to do it. The other way is, air can be considered an ideal gas. So we know PV equals nRT if it's an ideal gas. So if I want to know N over V, that is the number of moles divided by the volume, that's going to be just the pressure divided by R and T. You can also use this as M if you have the proper R, but in this case we were given the molecular weight. So we actually want to find the number of moles, and then we can convert that into mass. So in this case here, I want to do 2 times the atmospheric pressure in pascals. That's 101.325 pascals. Times 10 to the 3, right? Times 10 to the 3rd to have it in pascals as opposed to kilopascals, divided by our universal gas constant, and then our temperature in Kelvin. It has to be in Kelvin because this unit here is given in Kelvin. And this is not a difference in temperature. This is just one single temperature. So it's a state property equation that we're using. We use the ideal gas equation. So I got 8444, and this is moles per meters cubed, but we can check. We can check, and we should always check. So this fellow here on the top, that's pascals. Pascals. Then this guy here, that's the universal gas constant. So that's joules per moles per Kelvin, and then our temperature is in Kelvin. So these guys go away. We know that a joule can be further broken down into a pascal times meters cubed, and therefore what happens here is that pascals go away, and we're left with meters cubed on the bottom divided by moles. So moles go to the top, so this is moles per meters cubed. All right, now we want density. We don't want this fellow. We want mass over volume, not number of moles over volume. So I'm going to relate this property here, which is precisely the molecular weight, or the molar weight, as they said in the problem statement. So what I want to do is I'm going to think the following. Actually, let's just think about this without really, breaking a sweat. No memorizations. This is mass over number of moles. I can see it from the units. Okay, so the molecular weight is just my mass divided by number of moles. What do I want? I want mass over volume. So that means that if I want to substitute the number of moles, all I need to do is the mass, actually, that works? Yeah, that works. Divided by my molecular weight. Right? Now, I want to divide both sides by volume, just because I want to have, on one side, number of moles divided by volume, which is what we have on the other equation there. And over here, I have mass, volume, and then number of moles. So that means that if I have this, and I do have this, as long as I can multiply by the molecular weight, I can get the thing that I'm looking for. So what I'm looking for is, and so I did the wrong step here, part of the process. So number of moles by the volume multiplied by the molecular weight will give me mass over volume, which is the same thing as density, which is what I'm looking for. Okay, so density, that will be number of moles over volume. That's what we know already. So this guy here. Times my molecular weight, which is 29 grams, right? Grams per mole, and I want kilograms per mole. So I'm going to do 29 times 10 to the minus 3, so that I can have kilograms per mole. I left the units on purpose because then you can see that clearly this becomes kilograms per meters cubed, which is what we're looking for, which is great. Now, I honestly, excuse me, I honestly think this method, might take longer. So the other one is more straightforward, one that I left for you guys behind on the link before. But you choose whatever, rock or bolt, whatever you find to be easier. Let's go ahead and approximate this to 2, 3, 3, 3. Okay, cool. It's all good. Now we have everything we need. We have the density that we needed. We have the dynamic viscosity. We're ready to calculate Reynolds. So now let me just put this down here for us to do it. Reynolds. This guy is the one we just found out. So 2.333. The velocity is 5 meters per second. X, we want it at 30 centimeters. 30 centimeters, I'm going to do times 10 to the minus 3 to have it in meters. We're going to check units in a second. I'm dividing the whole thing by the dynamic viscosity, which I forgot already. Here it is, 1.86 times 10 to the minus 5. Cool. What did I get here? I got 188.145. And we shouldn't expect to have any units because Reynolds is dimensionless. And that will be our answer right there. Now let's just, before we sign off, let's just make sure that we didn't do any mistakes. So this is kilograms per meters cubed. Then we have meters per second on the velocity. I've converted the centimeters into meters, so this is meters. And dividing the whole thing, I have the viscosity. And if you don't remember viscosity, don't worry about it. You just look here on the table, and it's going to show you it's kilograms per meters per second. So kilograms per meters per seconds. Hopefully, it all goes away, and we're left with no dimension. So 1, 2, 3 meters, 3 meters in seconds, So brilliant. Good job. Green tick. And this is indeed our Reynolds number for this situation. All right, if you have any questions, as per usual, just let me know. If not, we'll talk soon.